All right, well, thanks so much for having us. Thanks for the introduction, Cindy and John, and thanks to the Water Research Center for organizing and for the seed grant that funded some of this research. All right, so I'm going to start this off. I'll be doing the introduction. I'll talk about how ecosystems influence aquatic plants. So why do they occur, where they occur? And I'll also be talking about the flip side of that. So what do plants do once they're in an ecosystem? And then Erin's going to talk specifically about the Yakima River, about water stargrass, why we have so much water stargrass, some general aquatic plant management strategies, and then he'll get into the specifics of the research he's been doing for his dissertation, looking at plant removal effects on oxygen concentration. So the first question is, why study aquatic plants? So about 100 years ago, Shelford didn't seem to think that this was a worthwhile endeavor and said one could probably remove all the larger plants and substitute glass structures of the same form and surface texture without greatly affecting the immediate food relations. So 100 years later, I think most of us probably disagree with that view. We're going to show today that aquatic plants can have a pretty large impact on the surrounding ecosystem. So how do plants get where they are in aquatic systems? So if you look at a terrestrial ecosystem, plants basically cover the entire surface except for some really extreme environments. But in water, especially in flowing water, that is not usually the case. And one of those big reasons is because of the hydrology, because there's that flowing water moving over the surface. And so over here on the left, we have a photo of a mountain stream. The water is moving very fast, and there aren't any vascular plants. There's some moss growing on the rocks, sort of clinging to those rocks, but only in the places where the water isn't directly hitting it, so sort of on the downstream side. And so in streams with really fast flows, you don't get a lot of plants because those propagules just get washed downstream. They can't settle down and put out roots. And if they do, they often get ripped out. So this can happen because there's steady high flows, or more commonly because there's big annual flooding events that would rip out any plants attempting to colonize. So in these fast flowing rivers, you're really only going to find plants on the very margins. We can contrast that with this picture on the right. This is a picture of the Yakima River. The flow is much slower, and you can see there are plants from bank to bank. So there aren't those high flows to rip them out and keep them from establishing. Another big control in aquatic plants is light. And so there's lots of things that can block light in aquatic ecosystems. So this first picture is showing a very turbid system. It's a system that's got lots of fine particles suspended in it, and that's going to block light. So it's going to be hard for plants to establish there because they need that light for photosynthesis. This is also true in deep waters. So think of a deep lake or a deep river like the middle of the Columbia River. That light's going to get attenuated by the water, and you're not going to get much plant growth. You can also get something called self-shading. So if you've got a bunch of plants that are growing up to the surface, they can create a canopy, and that can keep light from getting down below, and so you won't have plants growing below. If we think about the controls on light inputs as well, they are important. So it's not just the attenuation in the water body, but what gets to the water body. And so there's lots of things that control this, things like time of year, latitude, position in the network. And so just as an example, let's talk about the lower Yakima River, where we're going to be focusing today's talk. So the lower Yakima River is close to its confluence with the Columbia. It's wider. It's got a lot more flow going through it than the headwaters. And so it looks like this. We've got, during the growing season, there's going to be some shading from the trees that grow on the sides, but it's wide enough that most of the width of the river is going to get plenty of light. Now, during the winter, when those trees drop their leaves, there's even more light coming in, but we're in a temperate latitude, and so the days are pretty short. But the main point here is that in the Yakima, during the summer, we've got lots of daylight, many hours of daylight, and we have a wide river, so it can get to the river. Different patterns in different places, but our study site is going to be getting lots of light. So those were the controls on plants. There's other small things, but the primary ones are water flow and light. once plants get into a system, they can change things as well. So one thing they do is they slow down water. So water hits it, there's friction, and it slows down. And it can be pretty dramatic in some cases. This is part of the Yakima, where the water stargrass has basically slowed flow to the point where it's stagnant enough that it creates mosquito habitat. And they can actually do this in sort of this positive feedback loop. So when we have these slow moving currents, sediments drop out. So the little particles that are suspended in the water will drop out when that velocity slows. And when that happens, we have more water clarity. So it's removing those particles. And if we have more water clarity, we have more light, and now we have more plants. And so once they get in a system, they can change the system in such a way that preserves their ability to stay there and maybe even improves habitat for further growth and colonization. Aquatic plants also do some things like ameliorating nitrogen pollution. So they will be taking up nutrients. They need nutrients to support their body tissues, and they can take up nutrients from both the water column and the sediment. And so when you have a big plant population, they can hold nutrients like nitrogen and phosphorus, and then those nutrients are in the plant tissues instead of fueling algal blooms or moving downstream where they can cause problems. We've done some back of the envelope calculations in the Yakima, and the plants seem like a pretty large reservoir for nitrogen, so potentially some positive impacts there on water quality. The other big thing aquatic plants do is they influence daily oxygen patterns. So this is a typical oxygen pattern in an aquatic ecosystem. So during the day, oxygen is going to go up because photosynthesis is happening. So photosynthesis releases oxygen, it accumulates in the water, and we get a rise in that oxygen concentration. But at night, the only thing happening is respiration. Everybody has to respire, all organisms. So it includes plants. So the plants are respiring, the bacteria are respiring, and oxygen is getting consumed. And so oxygen is going to fall at night. And what aquatic plants can do is magnify that oxygen pattern. So if you compare the biomass of a whole bunch of plants to, say, the algae on the surface of a rock, or maybe suspended in the water column, there's just more biomass there. And so that means more photosynthesis, more respiration, and that means those swings get higher. We get higher highs and lower lows. And that can cause problems with having sufficient oxygen. So this is an example from the lower Yakima River in 2019, although subsequent years have had very similar patterns. And those plants are magnifying those windows such that our nighttime dissolved oxygen consistently falls below the Washington state standard for salmon. And so below that, the fish aren't getting enough oxygen. And that's hugely problematic for fish that want to try to spawn in the Yakima or migrate through to upstream tributaries. All right, I'm going to pause there and let Aaron take over. Aaron's going to tell you more specifically about the Yakima River and the conditions there.
All right. Thanks, Sarah. Okay, so the first thing I want to mention is that the Yakima River Basin is exceptionally vulnerable to climate change. So here's a map of the Yakima Basin. You'll notice the headwaters are up in the eastern Cascade Mountains. And as the climate warms, more winter precipitation falls as rain instead of as snow. And so the snowpack starts melting earlier. And so as a result of this, what ultimately happens is that historical peak flows, which might have occurred in the late spring or even early summer sometimes, shift earlier and earlier as the snowpack starts melting earlier and as more winter precipitation comes in as rain. And one other thing to consider is that the Yakima Basin is also heavily dammed. There are several large reservoir dams up in the headwaters, and reservoir dams can have the same impact in terms of shifting flows earlier. And and lowering summer flows. Okay, so let's go back in time a little bit. Historically, before the 1890s, we expect, we don't have hard data on this, but we expect flows typically controlled water stargrass. It's a native plant to the Yakima Basin. It's native in Washington. And historically, it was probably restricted to the margins just because scouring flows in the spring would rip it out of the sediment, and also for plants that weren't ripped out, just that higher sediment load that those spring peak flows carry and the deeper water attenuates light, and therefore the plant likely had less light. However, from the 1890s to the mid-1900s, those reservoir dams were built in the Yakima, and that lowered peak flows and also helped shift. Peak flows are also shifting earlier due to climate change, but also critically, agriculture was quite predominant in the Yakima Basin at that time, and most growers in the region tended to use flood irrigation. So they literally take water and flood irrigation water across their fields, which washes off lots of topsoil and nutrients, ultimately winding up in the river. So that meant that the Yakima River was very turbid, very cloudy. And so even though water stargrass had lower flows, which are advantageous, it also did not have a lot of light. However, in 1997, the Department of Ecology put a put a water quality improvement plan in place, and they got most growers to switch over to more efficient methods of irrigation. And within a few years, they managed to clean up the river quite dramatically. And within a few years, water stargrass started spreading. And by 2005, it was dominant in the river. By 2016, it was noted that at the majority of the river, quite a few places are covered by water stargrass bank to bank. It has very low flows, probably a high nutrient load in the sediment, and plenty of light for most of the summer. All right, so what I want to talk about now are some consequences of what has happened. And the first consequence I want to talk about is what has happened to salmon in the Yakima River. So Chinook salmon used to spawn in the stretch of river between the Tri-Cities and Prosser upstream, which is the section that's dominated by water stargrass. And critically, salmonids need spawning gravel. They need a place to lay their eggs, and they need that gravel where they lay their eggs to have plenty of oxygen for the embryos. And so as you can see in the animated GIF here, we've got a female salmon, and she's coming in, turns on her side, and you can see how she flips her tail and clears fine sediments in order to prepare for laying her eggs in her nest, what's called a redd. And one consequence of water stargrass spread is that not only are salmon redds now completely covered up by plants, but because, as Sarah said, because plants slow water flow and can cause sediment to drop out, that also increases the amount of fine sediment in the riverbed, which means that any potential salmon nests, salmon redds, don't get enough oxygen for the embryos. And so the historic salmon spawning grounds in this section of the river has been almost completely lost. Okay, so another consequence, Sarah talked earlier about dissolved oxygen, and dissolved oxygen in the Yakima River is quite low. So I pointed out that these, oh, sorry, I lost my mouse. There we go. So this line right here on the graph represents the Washington State Water Quality Standard for salmonids, about 8 milligrams per liter. Adult salmon typically need at least 7 or so to migrate, and oxygen, nighttime lows of dissolved oxygen in the Yakima typically drop between 4 to 6 milligrams per liter, depending on the season and depending on the year. What I want to do now is I'm going to take these nighttime lows and I'm going to plot them over the course of an entire year for multiple years. And this is what that looks like. So in the early season, from January through May and even through June, nighttime lows are above that water quality standard. However, as we enter the late spring and early summer, those nighttime lows start really plummeting, and year to year they drop quite low before eventually climbing up at the end of the season as physical processes like temperature and flow start to control oxygen concentrations. But the consequence of this is that for the majority of the summer, the Yakima River is inhospitable to salmon, not only because the river's salmon are cold water fish, and not only is the river too warm, but there's just not enough oxygen at night for their migration. And water stargrass is the likely culprit of this. In 2019, I measured its respiration and estimated that water stargrass in the lower river is responsible for about 90% of the respiration. And so what you see here on the right is that same this is the same figure you were just looking at. Again, oxygen drops quite low there. Let's go to Prosser, which is 26.5 kilometers upstream, about 17 river miles, if I remember correctly. And oxygen there at the river as it goes, just after it goes over a dam, which functions a little bit as a reset for oxygen in this reach, is low, but not quite as low. It tends to hover around 6 to 7 milligrams per liter. And between these two sites, there is quite a bit of water stargrass. And it seems that that water stargrass is just pulling that oxygen out of the river through its respiration at night. And by the time it reaches Kiona, it is extremely low. So I want to mention a few other consequences of water stargrass. For humans, for our society, it clogs irrigation intakes. It causes lots of problems. People don't like to float the river in the late summer because your feet get tangled up on water stargrass. As Sarah mentioned earlier, it creates mosquito breeding habitat. So the Mosquito Control Board locally is invested in finding if we can ameliorate this problem. As I mentioned, it covers up salmon redds. It also can create habitat for non-native predators. So non-native fish like smallmouth bass might be able to hide out in it and pick off juvenile salmon in the early season as they come downstream. And also what I'm going to focus on here is it creates really low dissolved oxygen concentrations, which are a serious problem. And I want to come back. This is the same slide I showed earlier, but I want to bring it up again because climate change is critical to consider here. So it's projected that low flow years are going to become more and more common in the Yakima Basin. And anecdotally, water stargrass biomass tends to be worse in low flow years. It seems to have more light, less potential scour. And so as those low flow years become more common, we expect the problems associated with water stargrass, including the dissolved oxygen problem, are likely to just get worse. Also, warm water holds less oxygen, so that problem is already being driven by climate change. So this is critical to address. So what can we do about problematic aquatic plants like this? Well, one thing we can do is we can take them out, we can manage them. And there's several potential methods of doing this. I'm going to talk about just a few of these and give you just a very basic overview of a few potential options. One of them is herbicides. However, unlike applying herbicides to terrestrial plants, there is a problem associated with applying herbicides to plants in flowing water, and that is namely that word flowing. The water is moving. Herbicides that you apply are will have less contact time with the plants. So that's a problem to overcome. There are some fast-acting herbicides. However, another problem to consider is the idea that water stargrass is a native plant, and many of those herbicides that could potentially be effective are illegal to use in the Yakima River. Either they're not allowed to be used in flowing waters, or they're only allowed to be used in the state of Washington for for plants classified as invasive that come from somewhere else. Also, herbicides can impose irrigation and drinking water restrictions. The Yakima River is used for both. It can potentially have sublethal effects for fish, so like reducing their reproduction. And One important consideration, though, too, is that when talking about herbicides, it can be done on a small or on a broad scale. So you might be able to do localized treatments to some side channels or some stagnant areas that function as mosquito breeding habitat with some slow-acting herbicides that have a smaller effect. Or potentially, it could be used across a broader area. But again, all of those caveats come into play that it's quite difficult to do so. Right. So another option is just to get in the river and pull it out. This is a fair with your hands, usually using rakes of some kind. This or some kind of weed rollers. This is relatively inexpensive in that it can be done by volunteers. All you need to recruit are people who are interested in conserving the river and get them to come out, wear some waders, give them a little bit of a safety talk and sign a waiver and get in. The permitting for this is relatively easy. However, it's limited to only shallow areas. You know, you can't have people working where the river is 6 feet deep. Not possible, nor is it safe. It's hard to get the roots out, so you often need to do some additional digging or to find a way if you want to get the roots, because again, it'll come back the following year. And something to consider, I'll mention this again, but water stargrass stems are very fragile. So it's really easy to rip off the top biomass and leave the lower biomass in place to regrow later in the season or the next year. And by default, this is limited to small scale areas. Sorry, the slide decided to, there it is. There we go. Sorry about that. Okay, so let's go up a little bit bigger in scale and we can use aquatic plant harvesters. So this is an aquatic plant harvester that the Benton Conservation District has purchased with a grant from Department of Ecology. And this is able to operate across a much larger scale. However, it is very time and labor intensive, and this cannot be done by volunteers. Therefore, it costs a lot more money. There's some difficulties associated with it, such as if you remove all of this plant matter, in this case, this particular harvester uses a pulling wheel. So ideally, it grabs that stargrass, pulls it out by the roots, loads it onto this conveyor into the boat, and you end up with a really heavy boatload of plant matter that has to be disposed of somewhere. So what do you do with that? You can pile it on shore. You might be able to lift it down, let it drift downstream, but that can pose some problems. And we'll talk about that in a little bit. Okay, so one last potential management method is to use flushing flows. And so this is the idea that we can attempt to recreate a little bit of that historical flushing flow that occurred in the early spring. And we might be able to do some dam releases from some of those reservoir dams and help scour out water stargrass biomass or suppress its growth just by decreasing the amount of light that it gets. There's some difficulties associated with this. First, I want to mention reservoir releases are already used in the Yakima Basin at certain times to cool off water for returning salmon. So this is a possibility that's been considered. One problem to consider is drought years. Again, climate change is making droughts more and more frequent. Therefore, this is going, the feasibility of this is something that needs to be thought of carefully. There may still be some other options, such as using localized releases in certain places that could be done even during a drought year. And this, of course, can operate at the scale of an entire watershed. We'll talk about that again in a little bit, but this potentially has the ability to most dramatically affect plants. Okay, so now let's move to some specific plant removal effects on dissolved oxygen. And I worked, so this is research I did in coordination with Benton Conservation District and Yakima Nation Fisheries. And we did 2 small pilot treatments to see if we would be able to affect dissolved oxygen. So my research partners here used an aquatic plant harvester, and I used dissolved oxygen sensors that look like this to monitor oxygen concentration at the upstream and downstream edges of the removal area. And so the first one we did was in 2023, at Benton City, or a site called Kiona. And so this is what the study site looks like. What you see right here in green, these are where the control sensors were. So these are the upstream sensors. They measure oxygen in the water as it comes into this section of the river. The blue here is the area of plants that were removed by the harvester. And then we had a sensor down here at the downstream end, in this case called the impact sensor. And so what I did was used an experimental method called a before-after control impact experimental design. So the conservation district removed about 23,000 square meters of plants, or plants across that area. And we've got sensors downstream of that area and upstream of that area. And what we do is we compare the relationship between the impact sensors at the downstream site and the control sensors upstream. And we compare that relationship both before the experiment and after the experiment. And if there's a change in that relationship, then it indicates that there was an effect. And the idea here is that oxygen in the river fluctuates naturally. It fluctuates from all the water stargrass upstream of where the control sensors are, plus for a lot of other reasons. So we need to know what oxygen is coming into the reach, and then we can look to see if we can change oxygen through this section. Okay, so let's look at some results. So what you're looking at here, this is nighttime minimum dissolved oxygen at the control or the upstream sensor in the purple, and the impact or the downstream sensor in the green. And before plant removal, you can see they're fairly different. The downstream sensor was consistently had lower nighttime oxygen than the upstream sensor did. Then we have a section of plant removal here in late August. And then for the first 3 weeks after plant removal, the two lines are closer together. So nighttime DO at the downstream sensor was closer to nighttime DO at the upstream sensor. And then there becomes a place where physical processes start to become dominant. So temperatures decreasing, flows are increasing, and these things start to take over DO, and pretty much all of our sensors in the river everywhere start to become pretty much the same. So DO is fairly homogeneous throughout this section of the river. Okay, but this figure is a little difficult to interpret if we want to look at the actual effect of removal here. So let's look at this a different way. And what I'm going to show you is a plot of what I'm going to call a delta DO, or delta dissolved oxygen. And by delta, I just means the change. So that is what we're going to do is we're going to take the impact minus the control sensor. And I'm going to show you how to read this chart first before I bring in the actual data. So because we're doing impact minus control just by subtraction, this horizontal line on the chart represents where minimum DO at the impact site is equal to minimum DO at the control site. Above this line is where DO at the impact sensor is greater than at the control sensor. And below this line is where nighttime DO at the impact sensor is less than the control sensor. And this gray line represents our plant removal. Okay, so let's bring in some data. And here's what we see. The mean delta before removal was negative 0.72 milligrams per liter. And then after removal, it was mean delta was negative 0.23 milligrams per liter. So on average, that's an improvement in nighttime dissolved oxygen of about 0.5 milligram per liter. Now, if you remember that previous figure at our nighttime minimums compared to the state water quality standard, 0.5 milligram per liter is not sufficient to improve oxygen enough for salmon. But it is meaningful that we were actually able to detect this. This is more evidence that water stargrass is actually driving dissolved oxygen. And it was just a pilot study. We removed plants across a relatively small area and we saw an effect. So this is great. So what we did the following year is we moved upstream to Prosser. So I mentioned there's a dam there, and this is upstream of that dam. And this is using the exact same study design. So we've got our control sensor upstream here, our plant removal area here. which was about the same size, about 26,000 square meters, maybe a little bit bigger, and an impact, or two impact sensors down here. We had one on each bank. Especially we did that because the river is just so wide here. The water flows very slowly through this pool. We weren't sure what oxygen would be like on both sides, and we wanted to see if we could have an impact on both. I want to emphasize something here, which is you can see the size of this pool here behind the dam and the size of the removal area. And unfortunately, my partners were not able to remove as much water stargrass as they were hoping to. They were limited to half days because dam maintenance operations were overwhelmed. There's a canal just downstream where they have to pull any plant biomass that floats downstream off the grate. And the idea here was that they intentionally let stargrass biomass float downstream using that pull and drift method so that they could get more done. But unfortunately, it overwhelmed dam operations, and eventually they had to quit. Okay, so I want to give that caveat, and I'm going to bring in some data. So here is nighttime minimum dissolved oxygen. This is the exact same type of plot you saw before, where we've got raw nighttime dissolved oxygen. We've got before removal here. Up at the top, we have our control sensor. Down at the bottom here, we have our two impact sensors. And I do want to point out something that's important to note is that right here, before removal, nighttime DO on the left bank and on the right bank are fairly heterogeneous. They're different. It indicates that the river here may not be completely mixed, and there's some water stargrass is likely having a strong impact on oxygen in different places, especially because it's just so wide. Okay, we have two portions of plant removal here, which are 3 days each. And then we have our period after plant removal. And eventually there comes this point where physical processes seem to become dominant, and nighttime DO was pretty equivalent across the reach, or across all of these sensors. Okay, so let's bring in that same sort of delta plot that we did before. Again, here, the horizontal line, we've got minimum DO at the impact site is equal to minimum DO at the control. Impact is greater than control above, and below the line is where impact is less than control. And unlike at Kiona, unfortunately, it looks like at first blush, there are no obvious impacts here to dissolved oxygen. This is just for one of the sensors. This is at the right bank. The left bank shows a similar pattern. This is kind of a preliminary analysis. I'm still working on evaluating these data. But I want to, again, as I pointed out before, the amount they were able to remove of stargrass is a tiny proportion of the stargrass that actually exists at this site between where our sensors were located. And so as you can see here on the so they removed stargrass here. This is a satellite image from 2018. In 2024, when this removal happened, this area in the middle here was also chock full of water stargrass. And there's all this water stargrass over here on the opposite side. So they removed a relatively small proportion. Okay, so I want to talk about one more set of data. And this is, we had the opportunity to observe a flow-driven plant removal at Kiona. So the same site where that first removal happened that I showed you. So what you're looking at here, this is a plot of discharge. So this is called a hydrograph. So these are water flows in the Yakima River at Kiona from 2012 to 2022. And what you can see is there's a lot of variability here, right? All the lines are just overlapping each other. Different patterns in different years, but every year, as we hit the late spring and early summer, flows drop quite low, stay low all summer long, and eventually start to rise again in the fall. And I had sensors in the river in 2021 and 2022. And in 2021, we had a low flow year with an early peak in discharge. In 2022, we had quite a high flow year. And notably here, it's not the highest flow that we've had in the last decade, but it was the latest high flow that we have seen in the Yakima at this site. And well, what happened with water stargrass? Well, these are USGS data of water stargrass biomass. And in 2022, sampling in August in mid-season and October in the late season, compared to previous years, water stargrass biomass was quite a bit lower than previous years where this had been measured. And just anecdotally, as I went to go put my sensors out in place in 2022, I looked around and said, where's the stargrass? It was just gone. It did eventually come back in later in the season, although not as abundant. And so here are what the DO data look like. So this is nighttime DO. In 2021 in the light blue line here, and in 2022, these are data from my sensors in the colored lines. And then for context, these three gray lines in the background are USGS data from 2018 through 2020. And notably, during the early season, when that stargrass biomass was much less abundant than it typically is, nighttime DO was on average about 1 milligram per liter higher than in 2021 and higher than is fairly typical during the early season. However, eventually, as water stargrass biomass started growing back by the mid to late summer, in mid-August, nighttime oxygen was relatively equivalent between the 2 years, and it seems to have followed roughly the same pattern as previous years. So what can we say about this? Well, high spring flows do seem to attenuate early season water stargrass biomass. And that does seem to drive higher DO concentrations. However, that biomass attenuation doesn't seem to have been sufficient to meet water quality standards. So if you notice, we're still, even though in the early season here, nighttime DO is much better than it was before, it's still well below this Washington State water quality standard line. Okay, one more thing that I want to show you with this. This is this is Prosser here in the blue line. So the dark lines for blue is Prosser, the dark line for green is Kiona in 2022, and the light lines in the same color are the respective nighttime DO from 2018 to 2021 as measured by USGS. There's a data gap here in 2022 at Kiona, but at both sites, nighttime DO was quite a bit higher than it had been in previous years. So we saw the same pattern at both sites. Okay, so let's talk about a few conclusions and kind of sum this up and give you a take-home message. First one, this is an urgent problem to deal with. Water stargrass is causing some severe problems in the Yakima River, and low nighttime dissolved oxygen is one of those. Mechanical plant removal does indeed appear to be able to improve low dissolved oxygen as long as, with the caveat that as long as you remove a sufficient proportion of plants. Flow-driven removal can be effective across a much broader area, but again, really at least until plants regrow. So if they regrow, eventually that advantage goes away. And so one thing that we might want to consider is not looking for the silver bullet here, but rather that we might look at doing multiple coordinated strategies to try to address this problem. Because it may be that not any one strategy will be effective for all the water stargrass biomass problems across the entire year. So one possibility could be to use flow-driven removal and to knock back water stargrass biomass in the early season. And then once it starts growing, we could hit stargrass with a harvester or other mechanical removal methods in the mid-season and try, or possibly in some localized targeted efforts or in possibly some problematic areas. All right. And with that, I would like to thank all of these people who helped, especially my fieldwork help, without whom I could not do this, and funding sources people who contributed funds to this from the Water Research Center, Benton Conservation District, Yakima Nation Fisheries, also grants from Department of Ecology and Yakima Basin Integrated Plan, and a fellowship with the Northwest Climate Adaptation Science Center.